There is nothing new to build today. That's not a day off. It's the whole point. The two structures promised, the stack and the queue, are barely structures at all. They're rules, disciplines you impose on things you already own. A stack is one sentence. You may only touch the most recent thing. A queue is one sentence. Things leave in the order they arrived. And the audition we set up, the array versus the list, comes with a twist. The job description is shorter than either resume. Both candidates can do the work. The interesting question is what each one charges. But before any of that, the deeper idea, because it's the reason these two run more production code than anything else in this course. When a structure can only be touched one way, every piece of code that touches it becomes predictable. You never have to ask what could happen to this collection. The contract tells you. That predictability is why these two are everywhere. The undo button, the call stack, the print queue, the message broker, all of it running on two one-sentence rules. Start with the stack and start with the rule. You may add only on top. You may remove only from the top. You may glance at the top. That's push, pop, and peek, the entire interface. Last in, first out. Now watch how much software falls out of one rule. Press Ctrl-Z in any editor on Earth. Every edit you make, the editor pushes the inverse of that edit onto a stack. You typed hello, it pushes delete 5 characters. You deleted a paragraph, it pushes the paragraph back. Undo is just pop. Execute whatever comes off the top. And the popped edit doesn't vanish. It gets pushed onto a second stack, the redo stack, and redo pops that one. Which explains a detail everyone has felt but never named. Undo a few times, then type something new, and redo stops working. Because a new edit clears the redo stack. There's no honest way to redo on top of a different history. Your browser plays the exact same trick. Back pops one stack and pushes the other. Forward goes the opposite way. And navigating somewhere new empties the forward stack. Same structure, same rule, same little heartbreak. So who gets the job? Here's the anticlimax. You already built a stack 3 lessons ago and called it something else. Take the dynamic array. Push is append. Write at index length, bump length. Order 1, amortized, with the doubling math from lesson 1. Pop is read the last element, drop the length by 1. Order 1, no asterisk at all. Peek is read index length minus 1. Remember what was actually expensive about arrays. Never the end. The front and the middle, where everything shifts. A stack never goes near the front. It lives entirely at the cheap end, the same hot cache line over and over, the access pattern the hardware loves most. The linked list auditions fine too. Push and pop at the head, 2 pointer writes each. But it pays a pointer per element, an allocation per push, and a cache miss per hop. To win a job, the array does with none of those. So every real stack you'll meet, Python's list, Go's slice idiom, the C++ stack adapter sitting on a vector, is an array touched only at one end. The discipline costs nothing extra. It's just a promise to never use the operations that were slow anyway. Now the marquee demo. The one piece of stack code every working programmer should be able to write from memory. The bracket matcher. Your editor runs it to rainbow your brackets. Your linter runs it. Every compiler that ever told you, missing closing brace, ran it. The question. In a string of parentheses, square brackets, and curly braces, does every opener have the right closer, in the right order? Here's the insight. The bracket you must close next is always the one you opened most recently. Most recent first. That is the stack's exact contract. So the algorithm is 4 lines. Walk the string once, see an opener, push it. See a closer, pop, and check the pair matches. Watch it run on. Curly open, paren close, curly close. Push curly, push paren. First closer arrives. Pop, it's the paren. Matches, curly close. Pop, the curly. Matches. String over, stack empty, valid. Now feed it. Paren open, square close. Push the paren. The closer arrives. Pop. A paren meets a square bracket. Mismatch. Reject. 3 ways to fail, and only 3. Wrong pair off the top. A closer when the stack is empty. Leftovers when the string ends. 1 pass. Order N. One more stack deserves its name spoken, because you're running it right now. Every time a function calls another function, the runtime pushes a frame, the local variables plus the address to return to. When the function returns, its frame pops, and execution lands exactly where the caller left off. That's the call stack. And notice it's the same insight as the brackets. The function you must return to next is the one that called most recently. Now call deep enough. 1,000 frames, 10,000. The push that runs out of room throws the most famous error in programming: stack overflow. Yes, the website is named after it. For now, that one beat is all we take. Lesson 9 opens this machine up properly. Frames, recursion, and why every recursive algorithm is secretly carrying a stack around. File the shape away, and let's meet the second workhorse. The queues rule is the mirror image. Add at the back, remove from the front. First in, first out. Align at a ticket counter, enforced by code. In queue at the tail, deque at the head. Both order 1. That's the contract on offer. And notice what the contract actually is. Fairness. Order preserved. Nothing skips the line, nothing starves at the back of it, which is exactly what you want the moment work arrives faster than you can do it. Your printer queues jobs. Your web server queues the requests it can't take yet. And at data center scale, the same discipline gets a grander name: the message queue. Amazon's SQS, RabbitMQ. One service produces work at its own pace, another consumes at its own pace, and a queue between them absorbs the mismatch. Billions of dollars of infrastructure, and the contract is still the line at the counter. One more customer to name, because it's coming. When this course reaches graphs in Lesson 17, Breadth First Search, the algorithm that explores level by level, ring by ring, runs entirely on a queue. The frontier of that search is a queue. Who implements it? This time the audition gets interesting, because the obvious answer is a trap. Take the dynamic array again. In queue at the back is append. Order 1, fine. Deque from the front, remove index 0. And there it is, the array's one forbidden move. Every element shifts left by 1 slot. 1,000 items waiting, 1,000 moves per deque. This isn't hypothetical, it ships constantly. Python, list.pop of 0. JavaScript, array.shift. Both look exactly as innocent as append. Both are one method call, and both are order in, every single call. Drain a queue of in items that way, and you've paid n squared over 2, the same quiet parabola that's been stalking this course since Lesson 1. The painter from Lesson 4 would recognize it immediately, doing the job from the wrong end, over and over. So the array, the candidate that swept the stack audition, stumbles. The stack only ever needed 1 cheap end. The queue needs 2, and a plain array only has 1. There are 2 real fixes. One you can already guess. The other is the prettiest trick in this lesson. The guessable fix first. The linked list, with a head and a tail pointer. deque at the head, inque at the tail, 2 pointer rights each. Order 1, no asterisk. It ships. But it pays the toll you know by heart now. An allocation per inque, a pointer per element, a cache miss per hop. The prettier fix keeps the array and kills the shifting with a question. Who said the front of the queue has to be index 0? Keep 2 numbers, head, the index where the front lives, and count. To deque, read the element at head, then just move head forward 1. Nothing shifts. The old element stays where it is, abandoned. To inque, write at head plus count, bump count. Both ends are now cheap because neither end ever moves anything. One problem left. Head keeps marching right and eventually walks off the end. So, Bend the array into a circle. When an index steps past the last slot, wrap it back to slot 0. Index modulo capacity. The freed slots at the start get reused, and the queue chases its own tail around one fixed block of memory, forever. That's the ring buffer. The contiguous layout lesson 2 crowned, wearing the queue contract, and not one element ever copied. Walk 1 to make it concrete. Capacity 8. Head at 0. Count 0. In queue 5 jobs. They land in slots 0 through 4. Deque 3. Head walks to slot 3. Count drops to 2. Slots 0, 1, 2. Free real estate. Now in queue 6 more. The writes land in 5, 6, 7, and then slot 0. Wrapped. The buffer is full, head sits at 3, and the front of the queue is in the middle of the array. Perfectly fine. The 2 numbers tell us everything, which leaves the one question every ring buffer must answer. What happens when it's full? 2 honest answers. Answer 1. Grow. Allocate double. Copy the elements out in query order so they unwrap flat into the new block starting at slot 0. Reset head. Lesson 3's amortized doubling, with a twist in the copy. Answer 2. Refuse. Return full and make the producer wait. That sounds like a failure. It's a feature with a name. Backpressure. A bounded queue is the system saying, slow down, I'm at capacity, which beats the unbounded alternative, a queue that silently eats memory until the process dies. Overload doesn't disappear just because you hit it in a queue. And this exact machine is load-bearing in tools you used today. A buffered channel in Go is a ring buffer, a fixed block, a send index, a receive index, a count, precisely what we just built. And when it fills, the sending Go routine blocks. Backpressure, built into the language. The Linux kernel's newest I/O interface is literally named for its 2 rings. One ring of requests from your program, one ring of completions coming back. Audio drivers feed your speakers from a ring. Network cards deliver packets into rings. Anywhere data flows between 2 parties at different speeds, there's a ring absorbing the difference. One party trick before the last structure, because it earns its keep in interviews. You can build a queue out of 2 stacks. InQueue pushes onto the first, deque pops from the second, and when the second runs empty, pour the first into it, pop by pop, which reverses the order on the way over. Any single deque might move everything, but each element makes at most 2 moves in its entire life, so it's order 1, amortized. Lesson 1's token bank, paying out again. One promise left to honor. The deque. Double-ended queue, pronounced deque, push and pop at the front and the back, all order 1. The greedy structure, both ends cheap. You could bolt a doubly linked list on, but the standard libraries do something smarter. The design teased when the list lost its verdict. Chunked arrays. Python's collections.deque. The C++ standard, deque. Both keep a chain of fixed-size blocks, contiguous inside, plus a small index of pointers to them. Need room at the front? Add 1 block at the front of the index. Nothing shifts. Walking it is mostly sequential and cache-friendly because inside every block, it's just an array. The list's flexibility at the ends, the array's locality in the middle. Both nearly free. And when do you genuinely need both ends? The flagship case is the sliding window maximum, a window gliding over data while a deque tracks the best candidates. That's not this lesson, that's the next one. And one structure you might expect here is missing on purpose. A queue where the line can be jumped, where the most urgent item leaves first, is a priority queue. And that takes a genuinely new machine. Lesson 15's heap. So, The workhorses and the real lesson underneath them. We built nothing new today. An array touched at one end became the undo button, the bracket matcher, the call stack. An array bent into a circle became the channel buffer and half the kernel's plumbing. The structures were already on the shelf. The value was the contract. You may only touch one end. In one end, out the other. Constraints aren't a loss of power. They're what make code you can reason about and systems that don't surprise you. Hold that thought, because everything coming next runs on it. So far, we've walked arrays one element at a time, one finger tracing the data. Next lesson, the first real algorithm patterns of the course, 2 pointers and the sliding window. The same arrays you've had since Lesson 2, but now 2 fingers walk them in choreography, and entire families of n-squared problems collapse into a single pass. The structures are built. Time to make them dance.